Hello everyone. In the last video, I discussed what a metric space is, and now I am going to discuss few examples based on it. But before that, let me recall what we had done in the last lecture. What is a metric space? So if we have a non-empty set, if X is a non-empty set, and D is a function from Cartesian product of X with X to R to the set of real number, then X with D is called a metric space if D satisfies few conditions. Four conditions D has to satisfy, and then it is called a metric space. Number one condition is non-negativity, which says that for every x and y in X, D of xy should always be non-negative. Second thing is identification, which states that distance of any two point t x y is 0 if and only if x and y are coinciding or they are equal. Third condition is symmetry, which says that d of xy is same as d of yx. Interchanging the element does not change the value. Number 4 is triangles inequality, that says d of for x, y and z belonging to x, d of xy is less than or equal to d of xz plus d of zy. So if D holds these four conditions, then D is said to be a metric and X with D is called a metric space. There can be more than one metric and there can be more than one metric space. Suppose we define some function and it turns out to be a metric, then X with D is called a metric space. Similarly, if we define some other function and it also turns out to be a metric on X, then we say that X with that function is also a metric space. So there can be many metric on a set and there can be many metric spaces. Now let us move to the examples. Question 1. If X is the set of real numbers and D defined from R cross R, that is X cross X to R, is D is defined as D of xy is absolute value of x minus y. This you have already done in case of distance between any two real numbers. So if we define this metric, then let us see is this a metric or not. So for D to be a metric, it must satisfy four conditions. So number 1, non-negativity. For every x and y belonging to R, We know that absolute value of x minus y is always non-negative. Therefore, d of xy is always non-negative. This is by definition only. Non-negativity condition holds by the definition of d itself. Second condition is identification. This is also trivially true because if I consider d of xy to be 0, this can only happen if and only if, by definition, dxy is mod of x minus y. It has to be 0, which is if and only if absolute value of some real number is 0, if and only if the real number inside the absolute value is 0. So x minus y is 0, and this can only happen, that is if and only if both of these values are equal. So identification also holds true. Now third condition is symmetry. If I consider d of xy, by definition it is mod of x minus y. Inside the absolute sign, if I interchange the places of x and y, will that change the value? No, it will not. So I can interchange and write it as y minus x. By definition of d, can I write it as d of yx? So d of xy turns out to be equal to d of yx. And therefore, symmetry also holds. Now the last condition, fourth one, is triangles inequality. Inequality. Triangles inequality. This is something you have already done as a property of triangles inequality in real analysis. If I consider x, let x, y, and z be three arbitrary values in the set of real numbers, then x minus y is, we can write it as x minus z plus z minus y. And when mod distributes on both of them, this will be less than equal to x minus z plus z minus y. Isn't it d of xy? It is d of xz. It is d of zy. Therefore, d of xy is less than equal to d of xz plus d of zy. So all four conditions are satisfied. Therefore, we can say that D is a metric on R, and hence R with D is a metric space. Also, this metric has a particular name. This metric is a usual metric on R. So that's it. We will do the next example in the next video. Thank you so much.